All right, so let's start. So yeah, and there is a last announcement. This course has been selected for showing what is co-learning by the administration. Now they put a lot of emphasis on co-learning, so students from different backgrounds, from international students, Japanese students learning together. And probably somebody will come in the future, I guess on the last lecture, but somebody will come and take some pictures. I will send you a message, please be here, because it's better if we are many students, if we have many students, but also they will take some pictures of the tutor-tutee pairs. So I will speak with them, with some of you who have a tutor-tutee pair. So it's good opportunity both for you and for this course to have this to be shown inside the university. Okay, last time, the first result I mentioned, well, it was not clear, but in fact, there was no mistake. So you can check, I corrected one mistake, but we introduced the notion of covariant derivative for manifolds inside Rm, and there are a few easy properties. In fact, it's really easy, but the way I presented was not very good. And one observation which we couldn't do at that time, but we will do it today, is that when we introduce this covariant derivative, remember, covariant derivative, if you have a curve, you have a vector field on this curve. So you have some vectors at every point on the curve. Let me take the green one. And the covariant derivative is you take the derivative. No, you start with vectors which are tangent to the manifold. When you take derivative, they might not be tangent. The derivative is maybe not tangent, but the covariant derivative is you take the component on the manifold. This is a notion of covariant derivative. And what we can observe, and we will observe today, it really depends only on the derivative of the curve. So instead of using this notation, as I introduced at the beginning, we change the notation. And in fact, we will generalize with this notation. So it's a new notation. It's covariant derivative on nabla and c dot, because this is a vector which is tangent to the curve, applied to a certain vector field. And okay, there are different notation, but then we extended it even in this framework. So we were for manifolds inside Rn. We extended it to nabla, one vector field and another one. And it turned out that this notation is a vector field, because when we apply it to a point, we have this covariant derivative of y, and the covariant derivative of y is a vector. It's a tangent vector. So it's meaningful. Before evaluating, you have a vector field, and when you evaluate at one point, you have just one vector. And still in this framework, we have observed two properties. What is when you multiply by a function on the manifold, the x, or when you multiply the y by a function. And these two properties are going to be useful because they will be used for introducing the abstract version of all this. So this part was for manifold inside Rn. Now, if you want to have a manifold which is not embedded in Rn, we define affine connection as this object, a nabla, which take two vector fields and send it to a new one. So it's a definition. You input two vector fields. So you have your manifold, you have two vectors field on this manifold. At every point, you have a tangent vector, and it gives you again a vector field, which is this one. And you take as a definition that it satisfies these two conditions. So these two formula, which I haven't written, but they have to satisfy these two properties. And we also define the notion of torsion, which is your T of two vector field, and it gives you a new vector field, and curvature, which when you apply for two vector field, you need a third one, and when you apply it to a third one, it gives you a new vector field. So it's called an endomorphism, because you need to apply one to get a new one, a new vector field. And if two properties are satisfied, we call this connection a Riemannian connection. The two properties are it's torsion-free. It means this is 0 for all x and y. And the second condition is the one written there. It's a compatibility condition because this scalar product involves the Riemannian metric. And you can see on the left-hand side, you have no connection. On the right-hand side, you have two connections. So it's a compatibility condition between metric and connection. And it turned out, this is a theorem, that on Riemannian manifolds, there exists a unique connection, which is a Riemannian connection. So it means which is torsion-free and satisfies this. So we are happy because when it's unique, you can always choose this one. And there is another formula which can be used for proving existence. It gives you an expression of this connection in terms of many other things. Now, when you use a chart, so if you use a chart locally, it turned out that this connection can be represented by m power 3 functions. So you have these gamma ijk, and for ijk from 1 to m, there are smooth functions on the manifold locally on the map. It turned out that if these two indices commute, it's torsion-free, and it's a if and only if. And for the Riemannian connection, we can even express, and I finished with this formula, we can even express this gamma ijk in terms of the metric. This is essentially the metric. It's expressed in it's a Riemannian metric applied to two vectors. So this is what we have done. Today we will finish. No, the first part is what is the use of this connection? Because so far I just defined it, but it has a very important role. And the next section is about geodesic. And yeah, if you have any question, you can always interrupt me. So let's continue. So what I want to introduce now is what's the use of this connection. So remember, connection takes two vector field, send it to a vector field, and it has some properties. Yes?
M locally, is that the same as the
No. Locally means when you take a chart. These functions, I gave some formula defined locally. So once you have your manifold and you took a chart on Rn, that's the meaning of locally here. Okay, so the use of connection. So I will first recall one formula. So we use of connection. And we will see that it's very useful. In fact, it's related to the parallel transport. So I consider a chart U5 so locally, and I consider a curve C from AB with image in U. Of course, you can patch different places, but it's easier if you have only one chart. And a vector field, which is a vector field also defined on U. Okay. And this vector field can always be expressed on a basis, because whenever you have a chart, you have a basis of the tangent space. So let me recall, it's a sum k1 up to m. We have k functions, and the basis of the tangent space was written like this. Whenever you have a chart, you have this family of vectors, which is a basis. And bk is a function, it's a smooth function on U. The coefficients of this decomposition. And now I'll just remind you that C dot of T was defined. It's a complicated thing. It was expressed by either pullback of this derivative, which is on the line on AB. And we can also decompose it. It's also expressed in, so it has some components. Because it's a tangent vector, the derivative of the or the c dot, the vector, which is the derivative of the curve, of the parametric curve, is a tangent vector. So it can be decomposed on the same basis, and I call the coefficient c dot jt. And it's a sum j from 1 to m. And for information, okay, Cj now is a smooth function defined on the interval AB. These components are smooth function on part of R. So C dot J are smooth function on AB. Okay, so this is the framework. And then I want to write a formula which I have already written last week. What is dy dt at t, the covariant derivative? I put two dot equal for the following reason is we defined this when it was inside Rn. Now we are in an abstract setting, so I haven't defined this notation. So I give now a definition. It's a connection at c dot of t, y. And I will write one more formula. So this has been defined in the abstract setting. So this doesn't need the manifold to be embedded into Rn, and I evaluated that. It has to be evaluated at C of t. Why? Because this is nabla of a vector applied to a vector field. So this is again a vector field, and you evaluate at 1 point. So I can write it maybe lower C of t. And the formula which I have already written last week in a slightly different, when we did use the formula for the gamma, it was at that moment I wrote a formula which was like this: t dot t3 I plus this jk. The gamma jk I at C of t, then bj of C of t times C dot. If you look in your notes, we had already such a formula, and EIE. So what is it? It's everything is a tangent vector at this point. So this P is CT. And what it is, there is a first term which is this derivative applied to a function, and I will still work on this a little bit. And then we have this is a number for each jki, and we have this component of y evaluated at CT, and this component of the tangent vector of the curve. Okay. And what I can still work on, what is this expression here? So let me just look at it. I recall this. So it's C star d over dt of bi, which it looks complicated, but if we look at the definition, this is nothing but d over dt of di composed with c. And let's check that it has a meaning. C is a curve, so it's defined on an interval with value in u. Then bi is precisely a function defined on u. So you end up with a function from this interval to r. You can take derivative with respect to t, well defined. Just a simple derivative of a function of one variable. And I can also write it as d over dt of bi of c of dot evaluated at t. And this is a nice thing with this subject. Things are rather complicated, but in fact, when you take a chart, things are becoming not so complicated. You are back to something which is a function of one variable. And now you can see something. Look at this expression. Of course, it depends on C of dot because this is where you are. But it depends only on the derivative of the curve at a certain point, which is what I had written here. I mentioned this covariant derivative depends only on the derivative of the tangent vector. It's visible here. The exact form of the curve doesn't matter. You only need the information, the point where you are, of course, and the tangent vector. The other things of the curve do not matter. So now we can justify with this formula what was written before about the covariant derivative, which depends on, yeah, it also justifies now this notation. This is really the only thing which appears. Okay. And let's keep this formula for a minute. So this is the covariant derivative in the abstract setting for an arbitrary vector field y and a curve which is on the manifold. And now definition. In this setting, so in this setting, in the note I'm a bit more precise. So it means precisely if we are in this setting here, y is parallel, it's the definition, is parallel along the curve, along C, if dy over dt at t is 0 for any t inside AB. This is the definition of y is parallel along a curve. The covariant derivative is 0. For now, it doesn't say so much, but it's a precise definition. So it means it's when this expression here is 0. Yes? I already mentioned, okay. It does, you could, first year you could complain, I haven't defined this. I told you there are two ways to do it. Either you take an open interval which is slightly bigger, and then this notion of C infinity is well defined and you restrict, or you define like I did once, on any domain you say that a function is differentiable if there exists a slightly larger domain on which it is differentiable, and you say I'm cheating, but that's the reality. Why I take it close? Because I want to say what is C of A. In the next statement, I will have the point C of A. If I only consider open, this is not meaningful. So I take on purpose a closed interval. This doesn't matter. It's not a big deal. So it means parallel. Oh, parallel. No, not parallel. Sorry, parallel. Is parallel along C if this covariant derivative, which is a vector, is a 0 vector. Okay, that's a definition for all T. And now the main theorem in this section, and probably if you Google parallel transport, you will see many pictures. You will see a curve like this. You start with a vector, and they are transported along the curve in this way. So what is the main theorem? So M, a Riemannian manifold, then we consider with the Riemannian connection. And we know that it's unique. I believe this statement is true for any connection, but I found it for Riemannian. And let's see from AB to M a smooth curve, So given x0 belonging to T of C of A, and now you understand why I want to have A. I take this time, this is C of A. So assume that you have only this vector. This is x0, which is at this point. The theorem says there exists a unique vector field which is defined everywhere on the curve. It doesn't need to be defined everywhere on the manifold. It has to be defined everywhere on the manifold. It's called a vector field. Vector field. Along C, I introduced this last time. The vector field along C, satisfying. It satisfies that at time or at a point, initial point, it's this one, and parallel along the curve, which is exactly this picture. So given one initial vector, there exists a unique way to transport it, satisfying this. Okay. And the statement is not finished, because now you can also take a second vector and take, for example, an orthonormal basis. And the statement is going to be, if you start with a basis, you can transport it on its stay a basis at every point. So still the statement, if F1P, when I already use this notation, FMP is an orthonormal basis, of sorry, I should not put P. I want an initial condition, so let me put 0. It's an orthonormal basis of T C of A M. So this is this initial basis. Then there exists a unique family F1C of dot up to FMC of dot. This is it's a field of orthonormal basis of orthonormal basis satisfying. The first one is a given one, so it satisfies f of 1 C of A up to f of M C of A is the initial one, F1 0 FM 0, and Fj, how do I write it? And Fj of C dot is parallel along C. So this is really this picture you should keep in mind. If you just have one vector, it can be transported like this, but if you have even a basis, you can transport the basis along the curve. So you start with one basis and all the other one are, there exists a unique family of orthonormal bases which have as an initial condition the first one, and each vector is transported parallel along the curve. And just one remark. I've assumed that the curve is smooth, but this is a bit too strong. And if you look at pictures on internet, the curves are not always smooth. Remark. It is sufficient that C is piecewise smooth. So what do I mean by this? This notion of piecewise is important. It means you accept a certain number of places where it's not smooth. A finite number. Don't ask me what about an infinite number. Probably we can do something, but I want to have a finite number. So this is a piecewise smooth curve. It's smooth except at a finite number of points. And you can still do the transport in this situation. If you start with a vector, you can still transport it parallel everywhere. So this notion of parallel along the curve is precisely the condition I have written before. This covariant derivative is 0, and the covariant derivative is written in terms of the connection. So the connection is used for this notion. The connection gives you the parallel transport. And you can still wonder, well, it's a consequence of this. Now, if you take an arbitrary vector in this basis, so I take an arbitrary vector on the first tangent plane, when you move it, its length and all scalar product are going to be kept. So let me write. It's a consequence of this statement. The proof is not difficult. As a consequence, the consequence of the previous statement, if t goes to x of t, so I change slightly the notation, because as I said, you don't need to know the vector field everywhere. So instead of writing x of c of t, I just write x of t. And take a second one. Two vector field along, no, two vector field parallel along the curve. So they are transported parallel along the curve. So the covariant derivative is 0. Then the scalar product, remember the scalar product is expressed in terms of the Riemannian metric. The scalar product of x of t, y of t, and this scalar product has to be evaluated at the point c of t. This quantity, the scalar product between, so this is a scalar product. These two vectors, they belong to t of c of t of m. So they belong to the same tangent plane. So you can do the scalar product, and it's in terms of the metric. This is constant, is independent of t. So it means the scalar product between these two vectors remain constant. As a consequence, what about the norm of one of them? Remember, the norm is the root of the scalar product as a consequence. norm of x of t, let me take the square, it's slightly simpler. It's phi c of t of the same vector. This is a norm square of this is constant. It's independent of t. So when you transport a vector along a curve, which means its covariant derivative is 0, the norm of this vector is constant. Do you have any question? So try to keep it in mind. We have manifolds, we have curves. We have one way to transport. So the vector is inside the manifold, so it's tangent to the manifold, but we have a way to transport it parallel in a precise sense. The covariant derivative is 0, so we transport. I'm not sure that it really means that it's point in the same direction, because we are not on a manifold inside R3. We are in an intrinsic way, but there is still a definition of what means a parallel transport of this vector. And if you transport it in a parallel way, the length is constant. Or if you take two vectors and transport them also in a parallel way, the angle, the scalar product remains the same. So the connection is very useful because all this is in terms of the connection. Do you have any question? Yes. I use the letter F because on a Riemannian manifold, when you have the Riemannian metric, you can define an orthonormal basis. I told you can do it because you have this notion of orthogonality, so you can define orthonormal. So I make a difference indeed between the basis which was given in terms like this. This one, it's true on any manifolds when you have a chat, but I'm not sure I can also normalize it because we have no scalar product. But when we have a Riemannian manifold, we have orthonormal. We can also normalize it by a Gram-Schmidt process, for example. However, you have to be careful. This one is well defined and it's smooth when you move from one point to another one. You have, okay, it has a precise meaning. If you just also normalize your basis arbitrarily on each tangent space, it's not clear that you have any relation between them. Except once you have this parallel transport, then we have more. But if you don't have this notion of parallel transport, you can define this on each tangent space, but they might not be related between the points. Okay? Yes?
Field of orthonormal basis.
Yeah, a field is a function with, in this case, with value in the set of orthonormal bases. That's why I wrote f of 1 c of dot up to f m c of dot, because it's a function defined on the interval AB, and for every AB you have, every point on this interval, you have a basis. So by definition, it's a field of orthonormal basis. Even though I've never introduced this name, at every t inside AB, you have an orthonormal basis. Okay, please observe one thing. Up to now, the curve was given. I had a manifold, or I have a manifold. I've given a curve, and I played with vectors which are transported along this curve. Now, the notion of geodesic is... Can you turn off your microphone, Martin, please? Okay. Thank you. What I'm going to introduce now, the notion of geodesic, is the curve is not going to be given a priori. We will choose a specific curve. So the notion of geodesics. 5.5 geodesics. So we are in this framework. We have a manifold. We have a connection. The connection was written like this. And I remind you that having a connection is the same as having this family of which are called Christoffel symbol. So connection is a family of Christoffel symbol. We are in this framework. So let me define what is a geodesic. Definition. So given, as I said, M Riemannian manifold and gamma, nabla, the connection, parametric curve. C on an interval, let me just write I precisely because I don't want to have the question, is it open or closed? This is interval of R. The curve is from an interval to M is a geodesic if d c dot over dt at any t is 0. What does it mean? Remember c dot, and I will recall it, but c dot is a vector field. It's a vector field along the curve. And I'm asking that its covariant derivative is 0. Okay. And now I can write in local coordinate what it means. So when you have a chart in local coordinates, it means this is equivalent to okay, in my note, there is probably an I. Yes, there is an I. Where does it come from? This is what I recall at the very beginning when I wrote, it was not for this one, it was for arbitrary vector field with, it was written in terms of the function bj or bk, but I had here something bj derivative, and here I had a bj and a c dot k. So now if I replace precisely y by its derivative, the derivative, now it makes two derivatives, and the y is also, the bj is replaced by cj dot. So it's just the same formula as before, except that I don't choose an arbitrary vector field y, I choose the tangent vector, and I end up with this. So a curve is a geodesic if it satisfies this equation. That's it. And what you observe that it's a second order differential equation. So this is a second order second order differential equation. And maybe you know something about second order differential equation. If you have two conditions, you have a solution. So you can still write in the or no, maybe no more in the definition, but right after, it's given a certain point P on the manifold and a set any vector which is in the tangent space as P, they exist. This is in fact the result of a theorem, the existence of solution. There exists a unique C. Be careful, it's maybe defined only on a small interval. C of 0 is P, and C dot of 0 is XP. So there is a theorem for existence of differential equations, which second order differential equation, which tells you on a small interval, there exists a solution, satisfying. Given an initial condition which consists in a point and a vector on the tangent space, there exists a unique curve which is a geodesic. So if you want to have a picture, you have a point P. Now at this point P, you have a tangent space which is just on the surface. Take on this tangent space a vector XP. And the statement is that there exists a unique geodesic on the manifold that exists. Maybe a just small one, but there exists a unique geodesic on the manifold. Okay. But be careful. What I want to say is the parametrization is important. What do I mean by this? If I just tell you, oh, this is a geodesic, it's not, this red curve is a geodesic, it's not sufficient. It's not just a curve which matters. It's the parametrization. So if you suppose you have this red curve on the floor, if I walk on it with a certain speed, or if I go faster, the two solutions will not satisfy this. If one of them satisfies this, probably the other one will not. So the parametrization is important. What I mean is two different parametrization. Given one parametrization of a curve, given one geodesic. So suppose one is a geodesic, a different parametrization of the same curve, a different parametrization of the same curve. In fact, I can be even very precise. The same a different parametrization of the same curve is a geodesic. If and only if, can you guess? If and only if. If you look at this equation, you could guess. There is no linear term. You have always a derivative. So the solution can accept a constant because when you take the derivative, the constant will disappear. So it means it's a geodesic if and only if the two parametrization differ by a constant. So So what do I mean by this? Suppose again I have this curve. If I start now and go at a certain speed, or wait for 5 minutes and then go on the same speed, the two solutions are geodesics. So you can accept a shift in time, but that's the only thing. If you go faster or if you go slower, it will no more be a geodesic. So in the notion of geodesics, it's not only this curve, what you see, but it's also the way you move on this, which is important. You have a question? Okay. First, you. No, you cannot rescale. It's not rescale invariant, and you can see it because they are not of the derivative are not of the same order. So you will not get something which is rescaling. It's only translation invariant in time. Yeah, but if you rescale, okay, I see. But your initial condition will not be the same. You will have to rescale also the derivative. So this is used at a certain point. But okay. Yeah, the rescaling plays a role in the next argument, but I think this result is correct. It's a solution for the same equation if and only if it's a translation in time. Okay, you prove it. You had another question.
Outside of this interval, or is it only in the interval?
Okay, I will speak about this interval in a few minutes. The statement tells you there exists an epsilon for which you have a solution. Can you extend it to a longer interval? If you're lucky. I don't know if you're lucky or not, but. Okay. It's always the same. On a given interval, it's unique. Now, it's possible that you can extend it, and then you will have a new function on a longer interval, and they have to coincide on the intersection. Theorem, what is missing here is a kind of uniformity in the sense that precisely I have no control on this interval of time. So it means if I take a different vector, if I take, oh, maybe not true. If I take a different vector at on the same tangent plane, then I will probably have another curve. But it might be that it's only defined on a much smaller interval. So I want to have some uniformity, and we will see why in this lens. So by a rescaling argument, we can do something. So rescaling plays a role for the next statement. So I don't think that, I mean, I read this statement about just difference in time, shift in time. So it's probably correct, but rescaling also plays a role. So, okay, let me do this picture a bit bigger. It will explain the next statement. So we have the manifold. I take a point P, and I will consider a neighborhood of P. I do it on purpose like this, just because it will be easier if I have enough space. But it's a neighborhood of P, so it's something open set containing P. And the statement is going to be, you can take any Q here, construct the tangent space at Q, take a vector in this tangent space, and there will be a certain geodesic, but with a length which is long enough. So we will see. So let's state this theorem. It's about the uniformity in this interval of time. So I consider M Riemannian. So Riemannian manifold with a Riemannian connection, manifold connection. And connection. I consider U phi chart. In fact, yeah, it doesn't really play a role, the chart. Now, what is for any P belonging to M, there exists a neighborhood of P. So this is this V. And a certain epsilon bigger than 0, such that. So given any P, you can find a neighborhood of P under epsilon bigger than 0, such that for any Q in V, any XQ tangent vector at Q with a size of this tangent vector smaller or equal to epsilon. So we restrict the size of this tangent vector. So the yellow arrow is not too long, but it doesn't depend on Q. It's uniform in this V. There exists a curve. It's going to depend on Q and on XQ. So I change slightly the notation. The time is the first variable, so I just put this, but it also depends on Q and on this tangent vector. So it's from the interval -2 to U with C of 0 Q XQ is equal to Q, C dot of 0 Q XQ is equal to XQ. It's really what I've represented here. And C of dot Q XQ is a geodesic. And there exists a unique C. So what we should keep in mind, you fix a P, but it means you take a neighborhood of P and an epsilon. And then for all points in this neighborhood and for all tangent vector of size smaller than epsilon, so this XQ is not too long, but there exists a unique geodesic which goes through this point and has this tangent vector. The point again is that if I choose a different Q, I do the same construction with another tangent vector. The geodesic is also more or less of the same length. This is what you should keep in mind. The interval -2 to 2 is the same everywhere. And the proof uses a rescaling argument, but plus some uniformity. Okay. So this is interesting, and we will use this in, okay. -2, 2 is completely arbitrary. If you prefer -3, 3, you can choose -3, 3. The thing is, this interval does not depend on the point you start in this neighborhood V. In the note, there is also another statement about the dependence on this curve. In fact, it's dependent, it's smoothly dependent It depends smoothly on the three arguments. So if, I don't want to write it, but if you slightly move Q, the new curve will be not so different. So if you change Q to another one, the new curve will be not so different. If you take a new vector, which is not so different, it will also be not so different. And if you change the time, of course, it's smooth also. So there is a statement which says it's smooth in these three variables, but in a precise sense, which is in the notes. So you have it's like the flow. In fact, it's a flow because it depends not only on one point, but it's valid for all points in a certain neighborhood. Now, why is this interval -2, 2? Because we are going to set, so in particular, I mean, this result applies also for the point P. So I can also choose the tangent plane here. So in particular for Q equal to P, I choose now this point, we set, I'm going to set exponential, it's a notation, exponential of xp is C of 1p xp. And 1 is in the interval, so it's meaningful. That's the thing. So what does it mean? And you should, exponential is not arbitrary. This notation is not arbitrary. So we have P, we have the tangent plane. We take a vector in the tangent plane, and we have this red curve I drew before. And I call a certain point, this point, I call it x of xp. In fact, if you have attended the course on group theory, it's quite similar to what we have between the Lie algebra and the Lie group. There exists also a notion of Lie, of exponential. So it means that we associate to a vector xp, we associate to this vector xp a point on the manifold, which I called xp, exponential of xp. It's a definition, and it's on this geodesic starting at p, or at least passing through p, and with this tangent vector. Okay. And it's called the exponential map. Now, remark, I want to compute something. Since, by definition, on a geodesic, this is parallel. By definition of a geodesic, this derivative is parallel along C. It implies that this vector, the norm of this vector, is a constant. And I told you there was this result. If you take a vector and do the transport parallel along a curve, the norm is constant. But what is this constant? You can take it at 0. Because it's constant, I can compute it at any place. And by definition of this geodesic, this is nothing but xp. Okay? Because the derivative of time 0 is this one. Okay. Thus, I want to compute now this length. What is this length? This is this length. And we have a formula for the length. What is the formula for the length of a curve? L is integral from 0 to 1 of phi c of t of x. No, sorry, it's c dot of t, c dot of t. This was formula for length of a curve. But this is nothing but the integral from 0 to 1 of norm of c dot of t, dt. And now this is a constant. It makes xp times the integral from 0 to 1 of dt. So it means the length of this curve is just xp. So with this exponential map, we have something on this manifold. On its length, this is a length. So let me write it here. This L is a length of the geodesic between P and the point X of XP. Okay, just a small computation. I sent you a message today. It's a nice topic. Yes. Between P, sorry, I forgot P. Initial point P and this exponential of XP. We prove it. This length is this. And now it's related to the rescaling remark. The map T goes to X of TXP. I can define this because the tangent space is a vector space, so I can rescale it. So it means if I rescale XP for T between 0 and 1. So if you rescale this, what you get all these points. So this map, the map T goes to X of TP for T between 0 and 1 gives a parametrization of the geodesic between the and X of XP. So we have even a way to have a parametrization of this. And do you have any question? So, okay, let's use this umbrella. What I'm doing, I fix the specific point here at the top. It's easier. So we have the tangent plane, which is a plane perpendicular to it. And what I'm saying is take on this plane a vector. According to the previous statement, this vector should not be too long. But if you take it with a size suitable, then you associate to any vector which is on this tangent plane, you define a curve. So if you take a vector on the tangent plane like this, you define a curve on this, which is a geodesic. But it's going to give us a parametrization of this surface very soon. Because think about it, if you take different vectors, we are going to have different geodesics, which on the tangent plane is vector space. You can identify it with Rm. So we are going to have a parametrization of this surface. So this is where we are going. And it's a natural parametrization. What is a star domain? Do you know what is a star domain? In Rn. Does anybody know what is a star domain? In Rn. Do you know what it is? It's a domain with a special shape. It has a point. Oh. Okay, this is a star domain. along this point. What does it mean if you take any point inside the domain and there is a distinguished point x0, the segment is inside. For example, if I take a banana, this is not a star shape. Oh, okay. Let me cheat a little bit more because otherwise it's going. Here you have no point such that if there is no x0, such that when you connect 2 points, you stay inside the domain. So a star domain in Rm with, so I call it omega, a star domain omega in Rm with, you need at least one specific point, so with distinguished point, distinguished x0 belonging to omega means that this linear combination x0 plus t times x minus x0 is inside omega for any x inside omega. This is a star domain. It has this property that rays are always inside. Okay. I can Google this, but this is the definition. x0 plus t is inside, sorry, for any t between 0 and 1. Because it's exactly the segment between 0 and x0 and t between 0 and 1. Okay, so I need this star domain. So let me now do an even bigger picture. We have our manifold. In white, it is a manifold. In yellow, it is a tangent space at P. And the next statement is that there exists a star domain. I can only speak about a star domain. I cannot speak about this on a manifold. Okay, the definition is in Rn or Rm. It's in a vector space because on a manifold, what means this? I mean, you would have to change the definition. So you have this P, the tangent plane, and the next statement is going to be this, any vector here or any element on this can be mapped on a domain on the manifold. So this is a domain on the manifold. So there will be a bijective map between vector here and the manifold. And what is going to be the map? It's going to be the exponential. This is x exponential x of xp. So let me state now what the result. And we are not so far from proving it precisely, but let me state it first. For any p belonging to M, there exists a U, a neighborhood of P. This is in M, which is diffeomorphic to a star domain. Star domain of Tp of M, which is which is a neighborhood. Oh, the 0. You should not care too much about the second part. It's quite natural. This tangent space, if I identify it with Rm, there is a 0 somewhere. And I'm just saying the last part of the sentence. So this is U. The set U, which is on the manifold, is diffeomorphic to the star domain, which is on the tangent space. And it's around. We have fixed on the tangent space the point 0 here. So we put the 0 here. So the distinguished point, I can choose it as the 0 of the tangent space. That's it.
Tangent vector.
No, but it's a vector space, so there is a 0 point. You can identify this tangent space. You can identify it with Rm. And this Rm has a 0 somewhere, and we put it at this point. And where does it come from? Remember, in the beginning of the story, I said that we choose some b smaller than epsilon at the very beginning. So this means these vectors are close to 0. That's the reason. If you construct all the thing before, in the previous statement, I said there exists a neighborhood of P. And now this neighborhood it contains a ball. And you use ball, and ball does the job. They are of small size and so on. So yeah, we are close to 0. That's it. And what is, so remember what is diffeomorphic? It means bijective. It's a bijective map and bicontinuous, which means it's continuous and its inverse, because it's bijective, is also continuous. The inverse is continuous. But so there exists this diffeomorphism between part of the manifold around P and a certain domain which has a star shape around 0. And the star shape comes from, just before I said we have a parametrization of the manifold. So whenever we consider a ray, it's called a ray, we go through the geodesic. Okay, I want to finish this construction. So we have this diffeomorphism, and now you can already guess what is the final thing. Here we are in the yellow part, we are in Rm, we have a basis. So it means I can consider a basis here, do the exponential of this basis, and it's going to give me a parametrization or a local chart of the manifold. So let me be more precise. So what we are in fact doing, and I put a picture, we are going to construct through the basis on the tangent space a chart on this part of the manifold, and it's called the normal coordinate neighborhood or normal chart at P. So let me finish this construction. So since now I use again this also normalized basis, this is an also normal basis of Tp of M. We can do it because we have a Riemannian manifold. Then xp, any vector, can be expressed as a linear combination, j1 up to m, xj, ejp. These are just coefficients. These are real numbers. We decompose it on this basis, right? And what we observe, the norm of xp, because it's an orthonormal basis, this is a one-line exercise, it's nothing but the Euclidean norm of, write it directly, x j square, j from 1 up to n, 1/2. This is the Euclidean norm of, I can also write it like this, x1 up to xm, Euclidean norm. It just, sorry? Oh, you are right. Thank you. Thank you. This time I thank you. Yes, it's on this basis. I decompose on this basis, otherwise we don't. This is also normal basis, so now it's correct. Yes, thank you. Good question. Good observation. I want to keep this. So then, and I'm going to set omega epsilon and define it as a set of tangent vector of size smaller than epsilon. So you can think about all vectors. We are on the tangent space here. I take all vectors which are of a size smaller than epsilon. Okay? I call this omega of epsilon. And I put this inside omega, and this one is given by the previous statement. The previous statement was this omega, which was this star-shaped domain. Inside the star-shaped domain, I put a ball. I can always do it. So I take epsilon so that this ball is inside the omega of the previous statement for epsilon small enough. But then take any phi. Oh, no, sorry. Take the exponential of all this. So it's now the exponential of this domain is something on the manifold. But inside, I have an exp of. It's a bit, no, in fact, it's not so complicated. You just need to realize what we are doing. Maybe I should separate the tangent space, put it somewhere else. Forget for a second, remove this, put the yellow part here. So we are considering a ball, all vectors here, and they are mapped on the manifold. I just separate the two things. I have the manifold, the point P, the tangent space. I just move it here. And the statement is that the previous statement that this was omega in the previous statement with a star-shaped domain was mapped bijectively on this domain. So this was a previous statement. Now I separate the two things. This is a manifold, and the star-shaped domain was mapped bijectively, and it was a diffeomorphism to a subset, which is a neighborhood of P. Now I take a ball, So of course, the image of this ball is going to be something slightly smaller. It is this exponential of, so do it again. We had this tangent space. We had this star-shaped domain, which was sent on the white domain. So I use the same color. So we have P here on the manifold. This is the zero of the tangent space. This is TP of M. This was the omega of the previous, and this is the image of omega. So this is exponential of omega. This was the previous statement. Now I'm claiming I take a small ball here. This is omega epsilon. Of course, its image is going to be slightly something like this. Again, it's bijective. And any vector inside this ball, any xp, I decompose it according to this decomposition. So I decompose it on a basis, right? So I'm taking any vector, this is a xp inside omega epsilon. I take it, I decompose it. Okay. It's inside this, and I define phi from this guy to, so this phi takes any element of this form and send it just to the coordinate x1 up to xm, which is inside the ball of radius, the ball centered at 0 of radius epsilon in Rm. Why is it inside this ball? Because look, this is a Euclidean norm, and I choose a norm to be smaller than epsilon. So I'm constructing a map from this yellow domain. So this yellow domain is x of omega epsilon to Rm. But this is a definition of a chart. That's why I use phi. So it means altogether we have the domain. What is the U? The U on a chart, it is this domain, x of omega epsilon phi is a chart. It's a map. We have to check that it's smooth, but it's by construction. It's a map from a certain domain around P to a subset of Rm. And it has a special name, of course. This is called, as I already mentioned, this, so x of omega epsilon and phi is called the normal coordinate neighborhood. I didn't use so much coordinate neighborhood. I use chart because it's shorter. Or the same as normal chart. And there is an exercise I mentioned. This neighborhood has nice properties. So exercise shows some nice properties. You can find this at many places. You know, it's a local parametrization with nice properties. And one of them that any Q inside this domain of omega epsilon can be linked to P by a unique geodesic, a unique which is not surprising because we started with geodesics. That's it. So any point in this neighborhood here can be linked to P by a unique geodesic. Do you have any question? Why do you want a cube? Then I ask you the question, why do you want a cube and not a ball? No, but you have this nice property of, we had a norm on the tangent space and it can be linked to this L2 norm which define a ball. You know, your cube is also one, you can also, it's also unit ball, but with a different metric, with a different norm. Take it, okay, it's a ball, it's nicer, smoother. Okay, it's almost finished this section, but I will not finish it today. But yeah, this part is really nice. So you have the notion of, today we introduce the notion of geodesics, and we introduce this natural link between a small part of the tangent space and a small part on the manifold. And it is through this exponential map. And yeah, this neighborhood has nice properties. There is a unique geodesic, and if you use this chart, you remember the Christopher symbols are defined with a chart. And it turns out that the Christopher symbols have a very simple expression in this chart. So remember when we defined the Christopher symbol, it was related, it uniquely defines the connection. This is true, but it's once you have chosen a chart. And it turns out that with this normal chart, things are, the Christopher symbols are quite simple. So next week we will finish this and we will start and very quickly go to a chapter which is about curvature. And I hope to keep one lecture or two lectures just to mention something about relativity, but it's a course on differential geometry. It's not about relativity.